Hey, welcome back. In this video, we're going to tackle finding the inverse of a quadratic function. In this case here, we're looking at f of x equals x plus 2 squared plus 3, specifically for the domain of x being less than or equal to negative 2. A really important point to make is that this domain restriction is absolutely necessary in this case. Because if we look at the domain, if we consider the domain of all real numbers for this function f of x is not 1-to-1. Our function here, f of x, is a parabola that's been shifted left 2 units and up 3 units when considering the toolkit function x squared. We know from this notation, which we call the vertex form, that the vertex is at negative 2, 3. And importantly here, it's not by chance that the vertex occurs at x equals negative 2 and we're given this domain restriction of negative 2, because this at the vertex is where we should split this parabola in order to create two halves that are both 1-to-1. Especially important in situations like this, it's important to define the domain and range before we do the work of finding the inverse, and you'll see why once we get to the work of the inverse. But importantly in this case, this quadratic with given this domain restriction here, would then have a domain defined from negative infinity to negative 2. This is directly this restriction given us right here. And then the range of this function isn't really influenced by this domain restriction, but it's influenced by the minimum value of this function. So this function outputs a minimum of 3 and then has only values above that or greater than that. And so the range for this is 3 to infinity. Before we do the algebraic work of actually finding the inverse function, let's look at a graphical representation of f of x here and think about what its inverse would look like. So the graphical representation is exactly what we'd expect. It's this parabola has a vertex at negative 2, 3, facing up because the a value here is positive. But importantly to this conversation is this function is obviously not 1-to-1 when we consider the domain of all real numbers. And again, the 1-to-1 visually or graphically can be seen by passing a horizontal line test. So if we could draw an infinite number of horizontal lines that pass through more than just one point on this parabola, meaning it's not 1-to-1. And importantly to remind you what it means to be 1-to-1 for a function, it means you only output a certain value for a specific input value. In this case, if we draw a horizontal line and we have 2 different points on this graph, what that means is that a certain output value or that y value is associated with 2 different inputs, which is completely legit for a function. A function can do that, but if it's going to have an inverse, it cannot have that situation. And to tie that last conversation in graphically, if we just took this full parabola and reflected it over the line y equals x, this new relation, this sideways facing parabola, would not be a function because it doesn't pass the vertical line test. Or in other words, there are many inputs that have more than one output. And that's the consequence of the original function not being 1-to-1. Though if we're in a case where we have to find an inverse function, what we're going to need to do is to restrict the domain. So if we take that full parabola and apply this domain restriction right here, that x is less than negative 2, and we just create a dotted line with the part we're not going to use. So the solid line here represents the part of the function we're focused on. The dotted line is the part that would be there if we didn't have this domain restriction. And then now we reflect that over the line y equals x. We can see that the result would be a function. All right, that's the conceptual setup. Let's now get into the work of finding this inverse. As always, what we're going to do is I'm going to replace f of x with y. You absolutely don't have to do this step. It just makes things a little bit less cumbersome as we do it. Then what I'm going to do the work of finding the inverse, I'm going to swap the x and y, or swap the inputs and outputs. That's exactly what the inverse function is. So I'm going to write this as x equals y plus 2 squared plus 3. Now my work is simply to solve this for y. I'll subtract 3 from both sides to get x minus 3 equals y plus 2 squared. Now what I'm going to do is apply the square root to both sides of this equation in order to get that y by itself. So I'll square root that. I'm square rooting it to cancel that square right there. What I get, importantly, on this side is plus or minus the square root of x minus 3. Again, whenever we have variables in an equation that we're trying to solve, we introduce a square root. We get these two answers, this plus minus. On this side, we get a y plus 2. Importantly, the consequence of this plus minus is this going to give us two answers. And I'll show that just in a half second. When I subtract 2 from both sides, I get negative 2 plus or minus the square root of x minus 3 equals y. So we've done the basic work of finding the inverse. The issue here, in which we would expect, and it's given that graphical representation that we were just talking about and the nature of parabolas, is that we actually have two options for our inverse. We have the answers of y equals negative 2 plus the square root of x minus 3, or we have y equals negative 2 minus the square root of x minus 3. So then in order to determine which of these two functions is the inverse of our function as defined, we use the work that we did with the domain and range a second ago. We know that for a function and its inverse, the domain and the range just swap. So what we know in this case, once we find our inverse function, is that the domain of the inverse is the range of the old function. So in this case, this domain needs to be 3 to infinity. And our range of this function, of the inverse function, is just the domain of the original function, which is negative infinity to negative 2. So what does that illuminate? Well, specifically, we can look at the range. We're looking for outputs that are less than negative 2 from this function. And if we look at both of these, importantly and beautifully, we see this negative 2 in both of these expressions. In the first case, we have negative 2 plus this square rooted amount, and then negative 2 minus this amount. And importantly for real numbers, whenever we square root an expression, we're always going to get 0 or positive, or importantly, non-negative. Meaning, in this case right here, we're going to take negative 2 and add 0 or a positive number to it. So these outputs will be bigger than negative 2. And in this case right here, this is negative 2 minus 0 or a positive number, meaning these outputs are less than negative 2. And when we look at again at our range here, we're looking for the situation where our outputs are actually less than negative 2, meaning this right here is the representative of the inverse of our original function. Therefore, given f of x equals x squared plus 2 squared plus 3, restricted on the domain of x is less than or equal to negative 2, we know that the inverse of that function on that domain equals negative 2 minus the square root of x minus 3. And finally, let's just tie this all together with the graphical representation. If we show the graph now of f of x restricted for x is less than negative 2, and then we also show the graph of this inverse function that we found, you'll notice that it does look exactly like this inverse function is the reflection of this part of the parabola on the domain of x is less than or equal to negative 2.